first thing we're going to talk about today is static charges. Does anyone know what static charges are? When your hair goes up. Yes, that's an example of static electricity. Yes, Brianna?
Static electricity is when a positive atom and a negative atom go at each other and they bounce off.
Oh, wow. When a positive atom and a negative atom go at each other, they bounce off. Very good. I can tell you're really good at science. You must have a great science teacher. All right. So let me give you an example of static electricity. Have you ever been on the playground and you went down a slide and you got a shock?
Yes.
All right. That's static electricity. And there's another really big example of static electricity during a thunderstorm. Anyone have an idea what that might be? Raina? Lightning. Lightning is a huge example of static electricity. So static electricity all starts with the atom. The atom is really small.
How small?
Wow, great question. How small is it, they ask? It is so small that 1 million of them could fit on the tip of this pencil. Wow. Okay, so the only thing smaller than an atom is what an atom is made out of. So the first thing an atom is made out of is something called protons. Say protons. And neutrons. Say neutrons. All right, say electrons. All right, the electrons are the smallest part, the most important part of the atom. And that's what causes the static charges. So what happens is inside the atom, the electrons are traveling around. And when there's something called friction, show me friction. When there's something friction, what happens is that excites the electrons, and the electrons jump, and you get a spark sometimes. So what's happening is the electron is leaving, and it goes onto the thing that you're rubbing against. So when you're going down the slide and you rub against the slide, an electron jumps from the slide and jumps on you. And you now have something called a negative charge. So what we're going to do now is I'm going to show you a really good example of static electricity. This here is called a Van de Graaff generator. Some people call it a static ball. So, you want to see some static charges?
Yeah!
All right. So what we see here is we see that the electrons are jumping from my wand to the Van de Graaff generator. Actually, from the Van de Graaff generator to my wand. Pretty cool, right? Let's check this one out here. All right, perhaps someone in the audience, a couple people in the audience would like to come up and do some static charges. You don't want to touch it, but nothing's going to happen. You want to start moving in slowly toward it, and when the friction builds up and the static charge builds up, you're going to see the jump of electricity. Okay, you start first, sir. Cool. Try to get it more toward the front so the people in the audience can see. Brianna, would you like to try it? Hand it nicely to Brianna. Thank you, Noah. Oh, you feel your hair going up? Well, maybe that'll happen in a few moments. Okay, let's give the two of them a round of applause. Okay, another really cool thing about static charges is what happens is this thing here is made out of rubber and plastic. And rubber and plastic is something called an insulator. So what's going to happen is if I touch this Van de Graaff generator and send electric charges through me, the insulator is going to cause the static charges to stay inside me. So then the electrons are going to want to leave. And they try to leave through pointy things like fingers and hair. So I'm going to need a few students to show how the electrons are going to try to leave your body. Okay, Gabby and Nevaeh, come on up. Okay, so let me show you what you're going to do. You're going to stand on the stage like this, and each of you is standing on the stage. And what you're going to do is you're going to face the audience so everyone can see you, and you're going to put one hand on. Don't do it twice like you do, okay? One hand on. Now, if you put one hand on, you will not get a shock. And even if you did get a shock, it's not really that bad. I don't want you to get a shock.
So if you keep the hand on, you won't get a shock, and what's going to happen is the electrons are going to go through your body and try to escape. If you decide you want me to turn it off, tell me, I'll turn it off, and then you move your hand away and you won't get a shock. Can you do me a favor and shake your head like this? All right, it's starting to go up, it's starting to go. Shake it crazy like this. All right, Gabby's is starting to go really well. Hey, Rita, come on up. Avery, I'm going to have you stand on here, and you're going to do what they did before. What's that? You're going to stand what they did before, put it on top. Jalen, I'd like you to stand over there and hold Avery's hand. And Andres, I just want you to hang out for a minute, okay? Avery, kind of shake your head a little bit. Oh, wow, look at Avery's hair. That's going up to me. That's getting up tall. That is going up well. All right. So what's happening is right now, the static charges are going from the Van de Graaff generator through Avery into Jalen. Andres, come over here. And I'd like you to go like this. And I'd like you to touch your finger. What happened? Why'd you jump? Why'd you jump? What happened? So you're telling me from all the way over there, the static charge has been through both of you and shot? That's incredible. And look at your hair. All right. Let's give them a round of applause. All right. Did you guys know the Van de Graaff generator? Yeah! All right. Those created some serious static charges. But this here creates even more static charges. That is called a Tesla coil. So check out these charges. Lights, please. Do you guys like that? Yeah! Alright, well I have another really cool thing. Does anyone in here know how to play the keyboard? How about that young lady back there in the pink? Come on up and come up these stairs here, please. Priscilla, give Priscilla a hand. And what song are you going to play for us today? Twinkle, Twinkle, Little Star. Okay, go ahead. Now it's my turn. What's your name? Alyssa. Everyone say hi, Alyssa. Hi, Alyssa. All right, Alyssa, today we're going to learn about density. Come over here, Alyssa. We're going to learn about density. So let me explain to everyone what density is. Density is a combination of mass and volume. So let's talk a little bit about mass. Does anyone know what mass is? You, sir. The weight. weight. Yeah, it's not, if you ask a scientist, they'll say mass and weight are not the same thing. However, they're very, very similar. So anytime you think of mass, I want you to think of weight. So when I say weight, I want you to yell mass. Weight. Mass! Weight. Mass! All right, and the other thing that density has to do is the size or the volume. Does anyone know what volume is? Yes, sir.
Space.
Is what?
The space.
The space, how much space it takes up, or the size. So if I say the size, you say volume. Ready? The size. Volume. The size. Volume. The weight. Mass. Oh, almost got you there. The weight. Mass. The size. Volume. The size. Volume. Weight. Mass. Size. Volume. All right, so when you combine the two, you get something called density. And what density is density is a combination of the two. Density is mass or the weight divided by the size. So something that is more dense is heavy for its size. Something that is less dense is light for its size. So what I'd like you to do, Alyssa, is look at these two spheres. Now, just using your eyes, which sphere do you think has less mass? The wooden one. She says the wooden one. Tell me if you agree.
Yes.
Yes, you agree. Okay, now I'm going to have you hold it. Now make an observation with your hands. Which one do you think now? All right, so the wooden one has less mass, and the metal one has more mass. So come on over here, in front. So they're both the same volume. They're both the same size, and she says that this one has less mass, and this one has more mass. Go ahead and put this into my handouts. Good. Step aside so they can see. Now, what do you predict is going to happen when you put this one on the other side? Right. She says this one's going to go up. Do you guys agree?
Yeah.
I think so too. Carefully put it in. Don't drop it in. Just place it in nicely. Okay. So absolutely. So the metal sphere has more mass. They're both the same size. So that means the metal sphere has more density. All right, so we're going to try something else while you're up here, if you don't mind. This here is a cup, and this here is water. Could you do me a favor? Could you pour water into my large cup? You can get almost to the top, definitely more than halfway. I'm getting thirsty. Okay, that's good. Go ahead and put the cap on that. And I'll go ahead and get these spheres. All right, so I'm going to give you the wooden sphere. When you place this in the water, what do you predict is going to happen? She says it's going to float. Do you guys agree?
Yes.
All right, go ahead and drop it in. Oh, she's correct. And what's going to happen with this one? She says it's going to sink. Do you guys agree?
Yes.
All right. Awesome. So let me tell you about density here. Water has a density of 1.0 grams per cubic centimeter. Things that are less dense than water tend to float, and things that are more dense than water tend to sink. Everyone give Alyssa a round of applause. Okay, so we're going to keep talking about densities. Solids are not the only thing that have density, but liquids have density as well. Mr. Burnos, can you get me 3 volunteers? Camden. This is a funnel. I'd like you to put the funnel inside my flask. And pour about 100 milliliters of water, so about up to here. 100, 150 milliliters. It's a very fluorescent green. Go ahead and keep going. A little bit more. Keep going. Keep going. Okay, perfect. Thank you, Camden. All right, Eduardo, come on over here. This is syrup. Eduardo, what do you think is going to happen when you pour syrup in there? It's going to flow. He says the syrup is going to flow. So what I want you to do is just take it and just go right to the top, and you can put a lot of syrup in there. Go ahead. That's okay. Keep going. Well, not all of it. All of it won't fit, but you can put a lot of it. Okay. Stop. Thank you, Eduardo. Very good. Let's go ahead and take a look at what happened so far. Can you guys see that? So what happened here is the syrup is along the bottom and the water is floating on top. All right, Priscilla, if you do me a favor, what you're going to do now is you're going to pour oil onto the top of that. You're going to pour it almost to the top, so pour it slow because it builds up quickly. Okay, stop. Excellent. All right, so what we have here is something very pretty called a density column. So Priscilla, which one went on the bottom? The syrup, the water, or the oil? Correct, the syrup went on the bottom. So in water, does the syrup have the most density or the least amount of density? It has the most density. Because I told you in the last investigation that things with more density tend to sink and things with less density tend to float. So which one has the least amount of density? The oil has the least amount of density. All right, give these 3 a round of applause. Okay, now this is something that you can do at home. At home, do you have syrup? Yes. Do you have water? Yes. I bet you have cooking oil. You don't need the food coloring. The food coloring just makes it look pretty. You can get food coloring, but this is something you can try at home. All right, thank you, you guys did a wonderful job. Okay, for the next science investigation, we're going to have a student walk on eggs. Do I have a volunteer to walk on eggs? Okay, you there. And bring 2 friends with you? Oh, I like your shoes. They're actually going to work out perfect for today. So come on over here. Come on over here. So here's what you're going to do. What you're going to do is she's going to attempt to walk on eggs. Now, what I want to know from you is every egg she steps on, are they all going to break? No. Some of them going to break? Or none of them? How many say that every one she steps on will break? Raise your hand. Okay, fair enough. How many say, well, not all of them, but some of them will? Yeah, that makes a lot of sense to me. And how many say none will? All right, we got a few for that. All right, so Taylor, here's what I want you to do. You're going to step flat-footed, like this, very carefully, flat-footed, all across the eggs, and you're going to walk on them. You 2 are going to hold her hands just to keep her balance. So, one of you come on, each one of you come on each side. That's okay. All right. So how do we do here? How do we do? How many broke?
1, 2.
All right. So 2 eggs broke.
3.
Pretty good, right?
3.
Not bad at all. Great job, Taylor. So now let me explain to you. I've done this many times, and a lot of times no eggs break at all. Believe it or not, a lot of times no eggs break at all. And let me tell you why. Actually, not yet. I need someone strong. No, I said someone strong. All right, someone strong. How about you there in the blue? You want to come up? Now, Cole, the egg is actually very, very strong. It's an oval, and ovals can be very strong. Right now, what I'm doing, don't do it yet, I'm pushing on the top and the bottom of the egg, and it's not breaking. So I want you to try it. I want you to press the very top and the very bottom of the egg, and, okay, are you putting some pressure on it? Is it breaking? All right, so let's make sure it's actually a real egg. So I have some paper towels right here, and Cole is putting a lot of pressure on it, and I hope you have a good aim. Well, what I want you to do is we're going to prove to everyone that that's a real egg. So he's putting a lot of pressure on it. Come over here. I want you to hold it from up here, and you're going to drop it. Go ahead. Cole, maybe they can't see. Is that a real egg? Yeah. All right, thank you, Cole. So eggs are oval, and the oval is a really, really strong shape. The oval is a very strong shape. They actually construct a lot of fixtures out of ovals. So this is something you can do at home. You can press on the top and the bottom of the egg, and you will find that it does not break the egg. Now, I would not do it over a couch or a carpet, but it's something you can take out in the kitchen and you can challenge your parents and give it a try at home. We just walked on eggs, and while we're talking about eggs, I'm going to go to the next investigation. but I do need a volunteer. All right, how many of you there in the red? Come on up. All right, so what I'm going to do, and you're just going to stand here really well. What I'm going to do is I'm going to now, this time I have a hard-boiled egg. Now, what a hard-boiled egg is, it's an egg that you put in water, you boil it for 20 minutes, and a chemical reaction happens to it, and it's nothing like the egg I had before. So I'm going to go ahead and peel the egg. And I'll make a bit of a mess here. So, you might have seen a hard-boiled egg before. If you've ever had egg salad or whatever, those are made out of hard-boiled eggs. So, Jace, what I need you to do is I'm going to get this egg to go into this container, but I'm going to use fire. Whoa. So, what I need you to do, Jace, is I need you, well, first of all, let's get you ready to look like a scientist here. Go ahead and put this on. That shows that I trust you, because this is a very, very important part of the investigation. So, Jason, what I'd like you to do is I'd like you to go back and I'd like you to get a fire extinguisher. Because any time you're working with fire in science, you have to have a fire extinguisher. Can you please go get it? Okay. That's not a fire extinguisher. Go ahead. Yeah, well, I guess you're right. That will put out a fire, but I don't think you have enough.
Need some help?
Oh, so I guess those would put out the fire. Excuse me, you stand on that side, you stand on that side. All right, that's not exactly what I meant when I said fire extinguisher, but I guess that would work. All right, so what I'm going to do is I'm going to light this match on fire. What are you doing? I guess I did. All right. New directions. Only if you see a fire. Okay. So I'm going to light this match on fire. And what? Hey! Why'd you do that? Yeah, I did light it on fire. All right, you guys are done. Get up. All right, so what I'm going to do is, and they're gone. I could not be happier. I am going to light this on fire. And I'm going to put this napkin here. And I'm going to light it. Yes, I'm actually doing a real fire. And I'm going to put the napkin. Okay, now I'm going to put the egg on top. Okay, all right, you two come on out. Okay, so let's give Jace and Will a round of applause. And thank you very much for getting me soaking wet. Okay, so obviously that was done for your amusement. Thank you, Jace. Thank you, Will. But in science, really, safety is always the number one priority. So I didn't really have an actual fire extinguisher ready to roll in case something did happen to go wrong. So safety first. Thank you guys. Round of applause. Yes, this is very exciting. I bet you've never seen a balloon blown up like that before. And I'm going to time it. So, okay. So, Ryan, what I have here is I have a wooden rod. And what I want you to do is I want you to put the rod through the balloon to go out.
I know.
You might? Okay. So let me explain to you how you're going to do it. You're going to take this rod right here, you're going to push it right there where the rubber is most thin, and you're going to get it in. Okay? Can you do that for me? Okay, what I'd like you to do is push it right through there. Okay, very nice. Now, what we're going to do is sit this up here, right there. Push it through again. Push. There you go. What do you guys think? All right, so let me go ahead and there you go. Okay. So the reason that works, rubber and plastic is made out of something called a polymer. And the molecules and polymers are really close together. So when Mariah pushed it through, what ended up happening is all the molecules came closer together and it kind of stopped the air from going out. So now I have an idea. I've done this with balloons. I've done this before, as you can probably see, but I haven't done it with water and a baggie before. So what I'd like to do is I want to be very, very brave. Fill a baggie with water, hold it above Rebecca's head, and have 5 of you come up and see if we can keep her dry. So Mariah, go ahead and have a seat. Thank you very much. 5 people. Go ahead and pour it inside. Now, I do think this is going to work. I mean, that's why I'm being so brave and having Rebecca sit there. All right, and then you just put a little bit more water. So what you're going to do is you're going to push it through, not pop it. You're going to push it through slowly. So make a line behind Amir. Okay, Amir, just put it right here. Wait, and just push. Keep going, all the way through. Go ahead. Push all the way through. There you go. Thank you very much. Next. Go ahead and walk to the other side of the stage. Push it. All the way through. All the way through. Good. Yeah. There you go. That's 2. You dry so far, Rebecca? Go ahead. All right. That's 3. Four, and 1 more.
The other way.
There we go. What do you guys think? All right, can you do this at home? You don't really have to put it above someone's head, but can you do this at home?
Yeah.
Absolutely. I bet you have water. I bet you have a bag, and maybe you even have pencil, even though you never have them in school. I'm guessing they're all at home. All right, round of applause for everyone. So the first energy I want to talk about is sound energy. And sound energy is the energy of vibrations. Go right here. Put your hand right here. And now I want you all to yell, sound energy! All right, great job. When you do that, you should probably feel your vocal cords vibrating. And vibrations is what causes sound energy. Now, we're going to talk a little bit about something called mechanical energy. Mechanical energy is the energy of motion. Put your hands above your head. Okay, so what we're going to do is we're going to bring our hands together, and that's going to be mechanical energy. Ready? Okay, out. Now what we're going to do is we're going to convert mechanical energy to sound energy. Ready? Mechanical energy. Sound energy. Mechanical. Sound. Now repeat after me. Mechanical. Sound. Mechanical. Sound. Let me hear you. Mechanical. Sound. Mechanical, sound, mechanical, sound, quick. Thank you. All right, so let's get a really good example of converting mechanical energy to sound energy. So let's go ahead and check this out. I have here my favorite garbage can. I bring it everywhere I go.
What?
I know. No, but this isn't even the cool part! Alright, so I'm using mechanical energy, sound energy. Alright, have a seat. Now I need my volunteers, and my volunteers are kids who are sitting nicely. Hands down. And do me a favor, balance this on your head. I'm sure you can do that. Balance it on your head. Just leave it there. Let me get a little bit more of my ammunition. is when you take one substance, put your hands in the air, you take another substance, you put them together, and you get something new. So let me hear you. 1, 2, new. Let me hear you.
1, 2, 2. 1, 2, 2. 1, 2, 2.
In science, anytime you're working with chemicals or anything other than water, we use goggles because safety is our #1 priority. Girls, can you please put the goggles on? This is a clear liquid, and remember, all clear liquids are not water. Some clear liquids can actually be very dangerous. So this clear liquid is something called vinegar. Say vinegar. Vinegar! Okay, actually I lied. Well, I didn't lie, but vinegar in your house, it's called vinegar. In the science laboratory, it's called acetic acid. Say acetic acid.
Acetic acid.
Nevaeh, will you please pour some acetic acid into my bottle here? I'll tell you when to stop. Okay, that should be enough. All right. Thank you very much, girls. If you can remove your goggles, go back to your seat because this is going to get dangerous. The other substance I have here is called baking soda. But again, it's called baking soda in your house. In the laboratory, it's called sodium bicarbonate. Everyone say sodium?
Sodium.
Bicarbonate.
Bicarbonate.
Sodium bicarbonate.
Sodium bicarbonate.
So what I'm going to do is I'm going to create a chemical reaction with acetic acid and sodium bicarbonate that's going to show you just how a rocket is really propelled. So a rocket uses chemical energy to start the liftoff. So what I'm going to do now is I'm going to take some baking soda and I'm going to put it inside a towel. Now this experiment is hard, and this is something if you do it at home, you want parents to help you. Do not do this without parent supervision. So I have here a bottle that the girls poured the acetic acid in, and I have baking soda here. Now what I'm going to do over here is I'm going to try to launch it across the stage. So, well, just watch. Let's see what happens. Okay, so I'm putting the baking soda there. I'm going to put my cork here. Okay, count down from 10. 5. 4, 3, 2, 1. And this chemical change is going to create something called an exothermic reaction. Exo means exterior, so on the outside, and thermo means heat. So it's going to create heat on the outside. So we're going to do something called elephant toothpaste. Alright, so it's called elephant toothpaste because after we do it, what happens, the chemical effect of it, it looks like very thick toothpaste an elephant would use. Alright, do I have a volunteer? Hi, Sophia. Okay, so the first ingredient for my chemical change is something called peroxide. Now, peroxide is something when I was a kid, and I was running around and I fell, and I got a scrape on my knee, my mom would put peroxide on it so it would clean out the cup. Sophia, would you do me a favor and please put on your safety goggles? You can take those off. And I'm going to put mine on mine as well. Safety is the #1 priority. Okay, I'm going to go ahead and pour my peroxide in. Okay, now this peroxide is a lot different than the peroxide that my mom put on my leg. That was something called 3% peroxide. And it's not very strong, it's safe for disinfecting cuts. This is 10 times as much. This is 30% peroxide. And this is, if this went on your skin, it would actually burn a little bit. So we're going to make it a priority not to get it on our skin. Alright, Sophie, would you do me a favor? And could you pour a little bit of water in there for me? Okay, stop. Perfect. And I want you to do me one more favor. You're going to put a nice little healthy squirt of Ajax dish soap in here. A lot.
Be generous. I'm not going to make you pay for it. Give it a nice big squeeze. Squeeze it hard. There we go. Okay, thank you, Sophia. Sophia, this time I'm going to have to ask you to go because this is going to get a little dangerous now. Thank you, Sophia. And I'm going to stir this like a scientist. All right. Now I'm going to take food coloring and I'm going to put food coloring in it. And I'm going to stir it again like a scientist. I'm stirring my glass. And I'm going to put food coloring on the outside. Okay, I'm going to take some green because I like green. Green is my favorite color. So there's a quiz on that later. And I'm making something here very, very pretty. Okay, cover my stuff. Alright, the other ingredient I have here is something called sodium bicarbonate. It's potassium iodine. So potassium iodine is a chemical only a scientist can get. And yes, I am a scientist. Okay. I'm pouring that into my water solution that Sophia poured for me. And I'm going to put this in here. And right now I have a mixture of a solid and a liquid. So what I'm going to do is I'm going to make a solution. A solution is when one thing dissolves in another. So I'm going to dissolve my potassium iodine into my water and make a nice solution. All right, and this here is a popsicle stick. Anyone can get those. Okay, so I'm going to put this here in the center here. If you all will count down from 10.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Here we go. Fire in the hole.
Oh, wow, check it out! Look at that thermal energy coming off of it.
It's solid.
Okay. Is Mr. Crouch signing